Hello everyone, my name is Romanpreet Singh Pahwa, and today I'll be discussing a paper titled A Survey on Object Detection Performance with Different Data Distributions. So the agenda for this talk is that first I'll be motivating the problem statement behind this work. I'll be discussing the data sets, in particularly the chart data set that we collected and annotated for this work, as well as the public data sets that we use for our experiments. Then I'll go into a bit of object detection history, the development of different object detectors, and the three chosen state-of-the-art object detectors for this work. After that, we'll basically follow up with various experiments that we do to highlight the gaps that are present in the object detection area, especially for robotic vision. And at the end, I'll basically conclude this talk and talk about some of the future works that this work can motivate. So object detection performance in the last 8 years has really improved significantly with the advent of large data sets as well as machine learning and deep learning based approaches. With convolutional neural networks, the computation has become very efficient, which has led to various deep architectures that can do the object detection much better than the classical hand-tuned detectors. So in this work, we want to investigate how this performance of these state-of-the-art detectors varies when there's a big shift in data distribution. How these object detectors perform when we mix these different data distributions for the same classes, or if we kind of sequentially add the data. So for this work, we basically collected data that we call chart dataset. We basically used a mobile robot, mounted several visual sensors on the robot. So we used Sony IMX IP cameras, we used the structure core camera, as well as the ICSR cameras for data collection. We divide the dataset into basically two mini datasets. We call them chart 1 and chart 2. On the left half side, you see the dataset for chart 1, which basically consists of data collected with an ICSR camera. And on the right side, you see the images collected from Sony IMX cameras, as well as the structure core camera. So as you can see visually, there is a big difference between the data that we're getting out of these two different visual sensors. Chart 2 data is a bit more dense, complex, contains a lot of radial distortion. The objects that you're looking for, like persons, beds, tables, they are a bit far away compared to the data collected and annotated in chart 1 dataset. So this basically induces this kind of a shift in data distribution due to different sensors, lighting conditions, radial distortion. To give a bit more details on the amount of data collected, for chart 1 we have about 800 images, for chart 2 we have about 1500 images. These data has been divided into train and test with roughly a split of 80 to 20, and the number of instances for beds and tables has also been provided. The joint dataset over here is essentially just a combination of chart 1 and chart 2. Essentially, the entire training set added together and the entire test set added together. So, for public datasets, we use Pascal VOC dataset, which consists of 20 classes. Overall, this dataset is about 10,000 images containing 24.5 thousand annotated objects. The other dataset that we use is MS COCO, which consists of 80 classes. 20 out of these 80 classes are exactly the same as the Pascal VOC dataset. And overall, MS COCO consists of 330,000 images containing 2.45 million annotations. These both datasets basically consist of a lot of outdoor images. Multiple instances of the same object can be present in a single image, and more often than not, most of the objects are basically located in the middle of the images. So we use three different state-of-the-art models for our evaluation. The first one is faster RCNN. Faster RCNN basically is a two-stage detector. So it has a region proposal network followed by the final detection classification. So it identifies some regions in the images that have a high likelihood of an object being present inside, and then basically improves over it in the next stage. It can give us up to 17 FPS and consists of 4 loss terms, 2 for each region proposed network and the final version. The second detector that we use is an SST mobile net v2. The classical SST network basically uses VG16 as a backbone, and it's a single stage detector. It's the mobile net v2 version is blazingly fast, can give us 59 FPS, and has slightly higher accuracy and almost equal to security for data set and faster RCNN. The third model that we use is YOLO v4, which stands for you only look once. It's also a single stage detector, and the version 4, after multiple improvements, basically gives us the best results across all these three models, and also has the highest speed. So for our experiments, we basically use the TensorFlow v2 OD API for our work for faster RCNN and SST mobile net v2. Because YOLO is not supported officially by the TensorFlow repository, we basically use kind of an unofficial YOLO TensorFlow repository for our experiments. So here are some visual results on individual training. So basically what we do over here is we train a faster RCNN model, SST mobile net v2 model, and YOLO v4 model on chat1 data, chat2 data, as well as the joint data. And the results are pretty good. The ground truth boxes are shown in green, our predictions are shown in red. And as you can see, they are almost overlap on each other with a very high accuracy. We can get even sometimes better than 98% MAP for all different models and for different data sets. And this is completely expected. So now if you look at the numerical results for joint training, as you can see, for faster RCNN, SST, and YOLO, the results are pretty good. We basically see really good results across chat1, chat2, and joint dataset. Now, if, as we see in the images before, if there is when the model is trained on chat1 and evaluated on chat1, the results are pretty good, with MAPs belonging to 98%, 94%, and so on. Same for chat2. When we train on chat2 and evaluate in chat2, the results are pretty good as well. Things start falling apart when we treat the models that were trained on chat1, evaluated on chat2. You can see that accuracy for faster RCNN go down from 94% to about 20%, for YOLO v4 from 98% to 40%. Similarly, if we had trained the model on chat2 and then evaluated on chat1, you can see the results dropping from 92% to 8.2%, or almost 100% to 36%. So this kind of shows that this data drift that happens between chat1 and chat2 significantly impacts the performance, especially for kind of a robotic application setting. We observe some similar drops in MS COCO and VOC datasets, but the drop is not as significant as what we see over here. So now, these are some of the results for standalone training, like the ones that the table that you saw before. So when we train on chat1 and evaluate on chat1, the results are pretty good, right? However, if we trained on chat2 and evaluated on chat1, you can see that the results don't make much sense, and it kind of misses all the bits for faster RCNN mobile net. And similarly, if we had trained on chat2 and evaluated on chat2, which is this over here, you can see the results are pretty good. However, when you evaluate on chat1 data, you can see that the results basically just completely fall apart as well. Now, the next experiment we do is that what if we added a little bit of data from the second data set into our training regimen. So the three different experiments we ran is when we had chat1 100% and chat2 10% data. And you can see that basically the results for chat1 are clearly still very high. However, for chat2, they went from like 20% MAP that we saw for faster RCNN to like 88% MAP. significant increase in performance. Not only that, we also saw an improvement in performance for chart1 data as well. So in fact, adding a little bit of chart2 data also helped performance in chart1. And we see the same observation when we basically reverse the splits, when we have 100% chart2 data and 10% chart1 data. The results on chart1 data significantly improve across all different models that we use, and our results on chart2 data also increase slightly. Another experiment we did was when we only had 10% data each, so just 10% of the images from chart1 and 10% of the images from chart2. The results, of course, are less or worse than if we had the entire data available to us, but the results are still significantly better. So to kind of compare them with the baseline, if we had the standalone training for joint data set results for evaluation, you can see that with just 10% extra data, our MAPs are basically improving very significantly for chart1, chart2, when we had only 10% of chart1 data as well, and only 10% each of chart1, chart2. So over here, of course, the results are slightly worse, but they're not significantly worse, even though we only use 10% of the total data. These are the visual results for joint training. As you can see that with 10% additional chart2 data, the results on chart2 are much better than before. Similarly, with 10% chart1 data in the training regimen, the results are also much better. Now, the next type of experiment we did is on both chart dataset as well as our Pascal VOC and MSCOPO datasets. So in this, we basically try to look into a problem where you had a model that you trained on one dataset, and then another dataset arises consisting of the same classes that you want to train, but there's a change in data distribution. However, at this time, you do not have access to the previous data. So while you have the model that was trained on the previous data, now you have to basically take that model as kind of a transfer learning approach and then train on the new data set. And how will the model perform now if we kind of apply it to the previous setting and the new setting? We use FastRCNN for these experiments, but the results for SST as well as for Euro were very similar also. So now, if we take the model that was initially trained on chart1 and then take this model, restart our training with chart2 data set, and then finish the training and evaluate it on the test splits for chart1, chart2, and joint, what we see is that on chart1, the model's performance significantly drops to 25% MAP, while for chart2, which the original model would not have performed well at all, the MAP does increase significantly to 87%. And similarly, if we take the initial model trained on chart2 and then trained it on chart1, the MAP on chart1 increases significantly but drops significantly for chart2 data. And these are the numbers for the baseline joint training if we had taken both the data sets together for training. And you can see that, for the new data that we're training on, the results are quite close over here and over here, but basically just completely kind of forgets the previous data that it trained on. And we see similar results if we take the model trained on Pascal dataset and apply to COCO and vice versa. Basically, the MAP performance on the previous dataset will drop significantly. And these are some of the visual results on the chart data. Again, to explain, basically pre-trained on chart1 and now we're training on chart2. So the results over here are not very good. Similarly, if we had trained the model on chart2 and then trained it on chart1, but the results on chart1 are really good, they are not very good on chart2. So this is kind of called catastrophic forgetting in controlled learning paradigm. And in a setting like this where you do not have access to previous data due to confidentiality issues, NDAs, or just having data from a previous project that is no longer accessible, this is a major cause of concern. So in conclusion, we presented our chart dataset. We discussed the 3 state-of-the-art object detectors that we use for our evaluations over here. We performed various experiments on chart dataset as well as public datasets to showcase the performance gap that can happen in a real robotic vision setting. And some of the future work as well as some of the conclusions from these experiments is that it is very critical to train on the new data if some sensors or class distribution changes. And this work also gives us a good motivation of looking into SSL based object detection and control learning based integration for the object detection paradigm. Thank you for your time. If you have any questions, please drop me.